All right, we can continue. Our next speaker is the third place winner at the Federal Award. Ziv Goldfeld from Gurion University, and his talk is entitled Semantic Security in the Presence of Active Adversaries.
Thanks. Before I start, I'd just also like to thank the committee and the Feder family for the award. And also I'd like to say thank you to my supervisor, Professor Chaim Permuter. Couldn't have wished for a better supervisor, so really, thanks. So I would like to start by saying that there are two prevailing approaches nowadays as far as security. The first is the cryptographic approach, which is also the dominant one in terms of applications, while the second approach is the information theoretic security approach, to which I will briefly refer to as IT security. And the latter possesses some very beneficial properties compared to cryptography, However, these properties are also accompanied by some insufficiencies, and reviewing these pros and cons is what I would like to do first. So, on the upside of things, IT security ensures protection versus computationally unlimited eavesdroppers, while cryptography is based on the fact that some mathematical problems are computationally hard to solve, an IT security protocol will stand versus an eavesdropper with the ability to solve such complicated problems, which is nice. And furthermore, in the presence of a noisy channel, IT security requires no shared key. That is, we can do without any common randomness between the legitimate parties while building on or exploiting the presence of the intrinsic noise that is natural in every noisy communication channel. And by exploiting the randomness of a noise as an additional resource of randomness, we can ensure security without a shared key. And as I said, these are both beneficial, both in terms of protection and in terms of cost. However, information theoretic proof that establish these two properties are usually derived under the assumption that Eve's channel is fully known, and most of the works also consider it to be constant in time, which is practically hard to rationalize or justify, because if Eve models an adversarial entity, that she won't be too happy to disclose any useful information to the legitimate parties, in particular not the statistics of her channel. So removing that would be nice. And furthermore, information theoretic security metrics, or the commonly used information theoretic security metrics, are insufficient, at least for some applications, as I will elaborate in a few moments. But for now, I'd just like to say that the goal of this work is, in a sense, bridging some of these gaps between cryptography and information theoretic security by taking IT security while moving to stronger metrics, removing this non-channel assumption, while preserving its benefits, as I stated before. And to do that, let's start by reviewing this so-called insufficient security metrics by considering the classic Wiretap channel, the degraded version of which was introduced and solved by Weiner in his celebrated paper from 1975, and generalized to the not necessarily degraded case 3 years later by Imre Chizer and Janusz Korner. And the scenario considers the transmission of a secret, random, and uniformly distributed message, M, of NR bits, that is encoded into a channel input sequence X, which is transmitted over the discrete and memoryless Wiretap channel to produce the two outputs Y and Z. Y is observed by the legitimate receiver and is used to estimate the message M, while the eavesdropper observes Zn and tries to use that as best as she can in order to understand as much as she can about our secret message. Now, in terms of security, our goal is to make it so that Eve won't be able to extract any information about the secret message, which can be formulated mathematically in several ways. And to give these different formulations or these different security metrics, let's consider a sequence Cn of NR codes. And a code is nothing but a pair of functions, an encoding function and decoding function, and they all work at the same rate R, which is not of too much importance for now. However, we get to say that this sequence of codes achieves weak secrecy, or the weak secrecy metric, if this normalized information leakage, and information leakage is just the mutual information between what's secret, the message M, and all that Eve knows, which is in this case is the sequence of observations Zn. And as I said, we get weak secrecy if this normalized information leakage converges to 0 as the block length grows. And although this was the standard in the first years of information theoretic studies, today it is basically widely accepted that this is insufficient for applications because if you think about it, although the leakage rate, and I'm saying rate because it's normalized, convergence, the eavesdropper can actually decipher an increasing number of secret bits as n grows, and this is clearly undesirable. So the trend, therefore, today in the IT community is moving away from this weak secrecy metric to now what is now referred to as strong secrecy by simply removing this normalization factor of 1 over n and demanding that the information leakage itself converges to 0, which essentially means that m and zn are asymptotically independent, which seems nice. However, still might be insufficient under some strict requirements of security because strong secrecy, we can say, sort of ensures security only on average. Sorry. And what do I mean by that? I mean that the convergence of this information leakage relies pretty heavily on the fact that we have a uniformly distributed message over an exponentially large message set where all the messages has positive probabilities. This helps the convergence. And you could, for instance, have the following scenario. You could consider the case where you have, say, 2 problematic messages, M1 and M2. And in case you transmit any of these messages, then the eavesdropper can easily decipher them. Okay? You could have such a situation while still obtaining a converging strong secrecy metric because the exponential size of the message alphabet and the fact that every message has positive probability kind of averages these bad messages out. A practitioner might say, however, that no, I want to know that I'm safe regardless of what message I'm transmitting. And this brings me to talk about the notion of semantic security, which is a further strengthening of the security requirement. Now, semantic security is actually a cryptographic notion, which is over 30 years old now. It was introduced in 82, I think. And I think it's safe to say, I hope Professor Uli Maurer won't be mad at me, that this is regarded as a gold standard in cryptography. And although I will not mathematically define that in cryptographic terms, I will heuristically say that basically what semantic security requires is the following. Not only that this eavesdropper's observation Zn should be useless in extracting information about this random uniformly distributed message M, it should be useless in extracting information about any arbitrarily distributed message, and even more so about any function of such message. A function being the first bit, the last bit, the even bits, the odd bits, or whatever you like. So if Zn is useless in extracting any information about any function of any arbitrarily distributed message, we have semantic security, which is sufficient, at least regarded as being sufficient for applications, but more interestingly, from our point of view, in 2012, it was shown by Beller, Tesaro, and Vardy that semantic security is equivalent to a convergence of the information leakage when it is maximized over all message distributions. And I would like to give 2 remarks about this very strict notion of security. The first is note that it at least solves the problem we had with strong secrecy. Because if you go back to these 2 problematic messages, M1 and M2, then although you might have a strong secrecy metric that converges, you won't have a semantic security metric that converges because one of the probabilities we maximize over is the probability that assigns positive values only to M1 and M2. So to get semantic security, you need to know that every subset of messages, however small in its size, as long as it's greater than 1, is secured. And furthermore, semantic security actually requires finding one sequence of codes, a single sequence of codes, Cn, that works well for all message distributions. That is, we first pick our sequence of codes, and then the eavesdropper may maximize over Pm when we still need to converge. However, finding such a single sequence of codes that satisfies so many security constraints at once requires stronger tools than the ones currently available in information theory. And to sort of answer this plea for stronger tools, I would like to introduce before you what we call the stronger soft covering lemma, which, as the name implies, is a stronger version of some existing soft covering lemma on which I will talk in a moment. However, this will be a tool that establishes semantic security for the Wiretap channel. It will even enable us to do a bit more. But for now, I would like to put the secrecy discussion aside for a few moments, focus on this guy, and then get back to secrecy and show you what we can do with that. So what's the soft covering setup? Sorry. Basically, we consider a point-to-point scenario without the second point, no decoder. We're not trying to decode anything. What we are trying to do is to take some collection of code words, to which we refer to as a code book, and choose one code word uniformly from it, which is done by this uniformly distributed random variable W that has nr tilde bits. And upon choosing such a code word, let's say we denote it by UN, we feed it into a discrete memoryless channel QV given U to produce the output sequence Vn. Now, this Vn clearly has some induced distribution by this random experiment over the entire block length that relates to the structure of the random experiment and to the fact that we have an underlying code book here. And this distribution is clearly not IID. However, the goal of this problem is to make this Vn resemble an IID sequence. And to formally, and how this exactly relates to secrecy, I will show in a moment, but you can think about it as if we could make the output at the eavesdropper look IID, then we're basically done in terms of secrecy. And to formally formulate this notion, let's have the following. So consider a random codebook, which is denoted by this bold Cn, which is nothing but a collection of IID random vectors, each of length n, indexed by W, where W spans over the aforementioned space of indices, and these vectors are independent across different W's. They have the same distribution, QU to the power of n, which is a product distribution, and a realization of this random codebook Cn is an actual codebook, which we use in our soft covering setup. Now, the choice of the codebook, as I said, induces some induced output distribution of the sequence Vn, which we denote by this green PVN superscript Cn, again, to denote its dependence on the underlying codebook. And we are trying to make this green distribution look IID. Like, what IID distribution are we trying to make it look? So, like our target IID distribution, which is denoted by QV to the power of n, where this QV is nothing but the marginal distribution of our coding PMF QU times our channel QV given U. Okay, so we're trying to make the green one approximate the red one, and essentially the question we're asking is how large should our codebook be, or in other words, how to choose the rate of the codebook R tilde so that the desired approximation holds. Now, this setup was solved under different distance metrics between distributions, and all the results basically say the same things. If the rate of the codebook R tilde is greater than the mutual information between input and output, U and V, then you have your approximation. Weiner originally derived this result in 75 in his common information paper for the normalized Kullback-Leiber divergence, which is not really a metric, but it can be thought of as a distance between distributions. Also sometimes called relative entropy. Later on in 93, Hahn and Verdu had it for the total variation distance. They also provided a converse. And recently in 2014, Hu and Kramer derived it for the unnormalized relative entropy. However, all these, as you can note, all these results relied on an expected value analysis. As you can see here, the expected value analysis with respect to the codebook, which is insufficient if that's semantic security you're after. And therefore, to strengthen the claim of soft covering, we had to move away from the expected value analysis to bring this stronger version of the soft covering lemma, which reads as follows. So if indeed the rate of the codebook R tilde is greater than this mutual information between U and V, and for now we assume that the output alphabet is finite, we believe we can remove this assumption, but for now we need it. Then there exist two positive real numbers, gamma 1 and gamma 2, such that the probability taken with respect to the random code generation experiment that this unnormalized divergence between induced and desired product distribution does not converge exponentially fast with gamma 1, this probability converges double exponentially fast with gamma 2. And having that, when combining it with the union bound, actually, you can derive the semantic security capacity of the classic Wiretap channel. But as I said, you can actually do even a few more things. And one of those things is give a solution to the open problem of the Wiretap channel of type 2 with a noisy main channel, which is, in fact, our main result. And I would like to use the time we have left to introduce this problem and solution. So what's that Wiretap channel of type 2? Like a sequel movie. It's an idea by Ozaro and Weiner from '84, where the channel between the legitimate parties is your standard DMC, QY given X. However, the channel to the eavesdropper is pretty unique. Eve is actually an active entity here in the sense that she can influence her observations, Zn, and she does that as follows. So Eve can choose any subset S of the indices between 1 to n that has size mu, which is given by the floor operation on alpha times n, where alpha is a parameter of the problem, a number between 0 and 1, and n is your block length. So Eve chooses any subset S constrained to a fixed fraction of the block length, alpha n, and perfectly observes the symbol, the transmitted symbols with indices in that subset. She sees all the xi's with i's inside S, otherwise she sees question marks. So for instance, if n equals 2 and to 10, and alpha is 0.63, and these were the transmitted symbols, then a possible observation by Eve is the following. She sees the 6 red symbols and gets question marks. Otherwise, and the thing with the wiretap channel of type 2, that is that security must be ensured, as we a priori don't know which subset Eve is going to choose, it should be ensured with respect to all possible choices of subset, which immediately introduces an exponential number of constraints, of secrecy constraints. And this problem, as I said, was introduced by Ozaro and Weiner in '84. However, they studied the noiseless main channel case, where this is an identity mapping. And under this scenario, they gave a full solution to the problem. They gave a single-letter characterization of the rate equivocation region, building on a pretty unique coset coding scheme in their proof of achievability. Now, the case with the possibly noisy main channel remained an open problem ever since, and a recent endeavor at it was made at the Lhasa SIT by Nefe and Yenner, that kind of built on Ozaro's and Weiner's coset coding construction to get a lower bound. They also had an upper bound, however, these bounds did not match in general. And I would further like to say that both these works considered only the weak secrecy metric. What we are able to do is, first of all, consider semantic security, which for the wiretap channel of type 2 looks as the maximized information leakage that should vanish when the maximization is over all choices of subset, but even more so over all choices of of message distributions PM. And under this rather strict notion of security, we're able to give a full characterization of the semantic security capacity, which is also shown to be equal to its weak secrecy capacity and is given by this term on the right-hand side, which itself is actually the secrecy capacity of the classic wiretap channel, to which I will henceforth refer to as a wiretap channel 1, with an erasure discrete memoryless channel to Eve with transition probability alpha. Okay, now what's interesting about it is that we show that coset coding is not really needed here. Your classic erasure wiretap codes achieve capacity. However, to show that, we do need our stronger tools of analysis in the form of the stronger soft covering lemma. And this is a nice thing to have because such wiretap codes, erasure wiretap codes, the binary version of those actually have practical implementations of efficient encoders and decoders, which is, as I said, is a nice thing. Now, what I would like to do before we are done is to show you some of the proof, some of the details of the proof. As far as achievability, I would like only to discuss on the security analysis. So, as I said, you construct a classic wiretap code, which also starts by introducing on top of your secret message M a dummy message W that is uniform over 2 to the NR tilde bits, and a wiretap code is just associating with each such pair M and W a code word XN. So our random codebook, as before, is just a collection of IID random sequences XN that are indexed by pairs M and W, independent across different M and Ws, and each has the same distribution QX to the N. And this could be thought of as an illustration of a wiretap code. For each specific secret message M, you have sub-codebook indexed by W. Okay, so before we can show semantic security, a preliminary step is needed, which is basically showing that our semantic security metric is actually upper bounded by this maximized divergence between the induced output distribution at the eavesdropper conditioned on a fixed message M, small m, and some target IID distribution. This divergence is maximized over all messages and all subsets, and furthermore is taken with respect to a reduced block length mu which is done basically by, you can always factor out the symbols where the eavesdropper sees a question mark. What's interesting about it is that this divergence is the exact type of quantity that stronger soft covering lemma can take into account when you consider the fact that for each message small m, we have a sub-code book indexed by W that corresponds exactly to the structure of the soft covering code book. So having that, just the union bound and the application of the lemma give you semantic security. We ask the question of what's the probability with respect to a random code book that semantic security does not happen? By the preliminary step, this is upper bounded by the probability of this maximal divergence not convergent exponentially fast, which by the union bound further takes us to the sum over all messages M and subsets S of each such probability of these divergence not convergent. And once again, because this is the quantity taken care of by the lemma, if we choose the rate appropriately, which in this case would be taking R tilde being greater than alpha H of X, gives you a double exponential decay of this probability. And when considering the fact that the combined number of messages and subsets, it's only exponential in the block length, you have 2 to the NR messages, and the number of subsets is upper bounded by the size of its power set, then this double exponential convergence provided by the lemma basically gives you semantic security. Now, having that, the rest of the details of the achievability are pretty standard. So from here, I would like to skip on to the Converse, saying a few words about that. The basic argument we make in the Converse is that the semantic security capacity of the Wiretap channel 2 is upper bounded by the weak secrecy capacity of a Wiretap channel 1 within an erasure discrete memories channel to Eve with transition probability alpha, which sounds trivial, but it's actually not that trivial because if you think about it, in a Wiretap channel 1 with transition probability alpha, by the law of large numbers, for large enough values of M, the observed subset of symbols at Eves will be approximately of size alpha n. But since this subset is chosen probabilistically, you have instances where Eve observes more xi's in the Wiretap channel 1 than in the Wiretap channel 2. However, being events with low probability, we use Sanov's theorem and the continuity of mutual information to get this not trivial but not too hard to prove upper bound and establish the converse, which gives us the result. So yeah, with that, let's summarize. So semantic security, as I said, is regarded to as a gold standard in cryptography, which is good enough for applications, was shown by Bellard, Tesaro, and Vardy recently to be equivalent to a vanishing information leakage when you maximize it over all message distributions. And to find code books that satisfy this requirement, we relied on our stronger version of the soft covering lemma that gives you a double exponential decay of the probability of soft covering not happening, which is useful in showing the existence of code books that satisfy exponentially many secrecy-related constraints or soft covering-related constraints, which can be thought of as the same or a related thing. And these two notions was combined to give a solution to this problem of the Wiretap channel of type 2 with a noisy main channel that was open until now. We derived its semantic security capacity, showed that it's equal to its weak secrecy capacity, and that classic erasure Wiretap codes are in fact optimal. And with that, I would like to conclude. So thanks a lot for the attention.